Differentiation is a technique that's used to find the gradient of a curve at any given point. So if we take a look at any curve, then obviously it has a different gradient as we move along the curve. And trying to work out what that gradient is, because only a straight line will have an exact gradient, is kind of difficult. So this technique was developed as a way of sorting out that problem. So the way it works from first principles is we've got a graph of y equals f of x, and we take a single point on that graph with an x coordinate of x, y coordinate of y, but we know a bit more about y because the curve is y equals f of x. So in fact we can call the y coordinate f of x. And we're going to say that the gradient at this particular point is quite similar to the gradient of this straight line, which runs from our original point to another point not very far away. And that point that's not very far away, we say has an x coordinate of x plus h, where h is just a little bit extra. What's its y coordinate? Well, its y coordinate depends on the function. So it's the function of x plus h. The gradient of any straight line is the rise divided by the run. So the rise is the change in the y values. So the greater y value minus the lesser y value, and the x is the change in the x values. So the higher x value, x plus h, subtract the lower x value, x. So what we know about gradient is that it's the change in the y values divided by the change in the x values. Now our problem with this is that we don't know what this h is. So how can we work out anything more detailed? Now, what was suggested by Newton and Leibniz was if h gets really small, so my 2 points are actually really close together, then the gradient of that line is pretty much the same. In fact, it will be, if we can make it infinitesimally small, the same as the gradient of the curve. So in order to do that, they developed a system of limits and said if we make h really small so that the 2 points are infinitesimally close together, then we actually get an exact value for the gradient. Now x plus h subtract x is h. So that's where this expression has come from, that the gradient, which we write as f dashed of x, or the derivative of f, is the limit of this gradient function. Let's see how it works with a particular curve. So if we've got the curve y equals x squared, we know what that looks like. And we take the point 416. We're going to use the same idea to find the gradient at that point. So we're going to move a little bit further on to 4 plus h, and then its y coordinate is its x coordinate squared. Then we're going to use the formula that the derivative, or the gradient, they've called it g gradient, is the limit as h tends to 0 of the change in the y's over the change in the x's, which is always just h, because that's how we've set it up. So we need to expand this bracket. So if we expand 4 plus h all squared, we get 16 plus 8h plus h squared. Then we're going to subtract the original y value and divide by h. So 16 subtract 16 is 0. So we're left with 8h plus h squared divided by h. Every term has an h, so we can divide throughout by h to give us 8 plus h, which is what we were asked to do in part A. Then, as h gets really, really small, this whole thing becomes 8 plus something so infinitesimally small that you can't see it, and therefore is just 8. So the gradient at that point is 8. So that's how we can do it for a specific curve or a specific point. Let's look at a curve where we haven't got a specific point. We're just going to take any random point. So x cubed, there's x cubed. So there's my first point, which is x and x cubed. And my next point a bit further along is x plus h and x plus h, all cubed. So the formula says the derivative is the limit as h tends to 0 of y minus y over the change in x, which is always h. So if we expand our cubic, we get x cubed plus 3x squared h plus 3xh squared plus h cubed. Then we're going to subtract x cubed and divide everything by h. So the same pattern happens. X cubed subtract x cubed gives us 0. So we've got the limit as h tends to 0 of 3x squared h plus 3xh squared plus h cubed, all divided by h. And every term has an h, so I can divide through by h. And I get 3x squared plus 3xh plus h squared. Now, as h becomes really small, this h becomes really small, so the whole thing here becomes really small. And h squared becomes really small. So actually all I'm left with is 3x squared. Everything else has gone to 0. So we end up that f dashed of x equals 3x squared for whatever value of x. And that's exactly what we would expect from the rules we've learned about differentiating polynomials.